Today we're going to look at our first type of simple machine in detail, and that is levers. So by the end of this video recording, hopefully you understand the anatomy of a lever, and also you'll be able to calculate something called the mechanical advantage of a lever and how much effort might be required to lift a load. First, let's learn how to classify levers. In general, there are three types of levers that we need to be aware of. A first-class lever, a second-class lever, and a third-class lever. Now, this classification system is dependent on three things. The fulcrum, which is the teetering point of the lever, the effort, which is what we put in, and the load, which is something that we usually lift. So a first class lever would have the fulcrum in between the effort and the load. For example, scissors. We would put our hands here to apply the E for effort. The fulcrum would be here in the middle where the nut holds the two blades together, so that's the fulcrum. And our load is whatever we're trying to cut, so class 1. Next, a class 2 lever would rearrange these three so that the teetering point or the fulcrum would be at one end, the load would be in the middle, and our effort at the other end. So now you'll notice the length that our effort is being applied is this, and the length of the load is this. Sometimes we call these arms. So from the load to the fulcrum would be called the load arm or the LA, and the effort to the fulcrum is called the force arm. A can opener or a bottle opener, as used here, might be an example of a class 2 lever. Here is the fulcrum where it teeters. Here is where the load is, and our hands go here. And so E, L for load, F for fulcrum. And our final class of levers is a third class lever, fulcrum, effort, load. For example, tweezers. Here is where the tweezer is pivoting, so I'll draw my triangle, so the fulcrum is there. The fingers apply the E for effort, and whatever you're trying to pull out, like a hair, ew, gross, that would be the load, L. Here's another look at it. Class 1, Class 2, and Class 3 levers. Let's look at the Class 3 lever for a minute. From the fulcrum to the load, we call the load arm, and it's pretty long compared to the force arm. So here's our effort to the fulcrum. We would call that the FA, the force arm. Our bodies have different classes of levers, and so let's see if we can analyze our bodies for a minute. Let's look at the arm. Although we don't know it because our skin covers it, our muscles usually attach in front of our joints. So for example, if you're lifting something, let's say this is a weight or a box, it's the load. Sometimes it's called the R for resistance. Our muscle is the effort, and look where it's attached. Here's where it's pulling, so not behind. And here's our fulcrum, and that's the pivoting point at the joint. And so if we look at that, R or L, fulcrum, effort, load, that would be class 3 lever. Let's look at this picture. So we're on our tiptoes like a ballet dancer. the load is right here, our body, and this time our muscle is attached here. So this would be a class 2. And when we're chewing food, we might consider the following. The resistance is the food in our mouth. Our jaw is the fulcrum. And sorry, not when we're chewing food, when we're lifting our head. Yeah, class 1. Let's see if you can identify the class of lever. We've already done tweezers, so that's class 3. How about this that's breaking open a walnut? Fulcrum load effort. What class of lever would that be? Fulcrum load effort. That's a class 2, like a wheelbarrow. Let's look at this hammer. It's trying to pull out the nail. So here is where it's resting on the bench. There's our fulcrum. The nail is the load. And we apply our effort of our hand kind of way over here with our elbow. So that would be a class 1 lever when it's used like this. And next, I want to deal with mechanical advantage. The mechanical advantage by definition is when we compare the ratio of how much force in newtons the load is compared to how much force we put in to the lever. So let's look at these pictures. Here's a class 1 lever. Let's say the fulcrum's right in the middle. Let's say we push down with 10 newtons and we lift a 10 newton load, a 10 newton box. What would the MA be? Well, the MA would be 10 divided by 10. So 1. Well, that's no good. That would mean we're just changing the direction of the force. Let's look at this one though, class 2 lever. A class 2 lever, let's say we push up with 5 newtons, so our effort force is 5 newtons, and the box, the load, is 10 newtons. Let's see, MA equals 10 newtons for the box, because that's the load force, divided by the effort force, which is 5 newtons. 10 divided by 5, the MA would be 2. In other words, we've multiplied our force 2 times. We can lift twice as much. And let's look at a class 3 lever. The load is 10, our effort is 20, so let's find our MA. MA equals 10 divided by 20, that's 0.5. 0.5. Whoa, what does that mean? We have to put in twice as much effort to lift the box, but we gain a speed advantage. All class 3 levers, believe it or not, have an MA of less than 1, which means for class 3 levers, we have to put in more effort than what we get out of it. Let's see if we can do some calculating now. Okay, here's our lever. We're going to put our box right here on the end. The box is 4 newtons. We're going to push down here, so there's our effort force, E for effort. Our load is going over here. So what does that mean? Well, here's our load arm to there. Here's our force arm. What do we notice about the distances? Well, the load arm is really small, the LA, the load arm's small compared to the force arm. Okay, let's calculate the MA. MA is the amount of effort here, the effort force, over the load force. Well, we don't know these right now, so there's got to be another way we can find this. We know what the load is without, so this box is 4 newtons without the lever. Well, a second way you can find the MA of a lever is to take the length of the load arm and divided by the length of the force arm. Or sorry, the other way around. Other way around. The force arm, its length, the FA, the length of the force arm, divided by the load arm, the LA. So let's look at our lever. We have 5 meters from here to the fulcrum, and that's our load arm. And we have 10 meters from where our hands are to the fulcrum. So that would mean the MA would be 10 meters, or 10, divided by 5. And that's 2. So 2, what does that really mean? We can double our force. That's what an MA means. If the MA was 3, that means whatever effort we put in on the other end of the lever, we'd get 3 times the force. Kind of like hydraulic presses. So let's see if we can find out how much effort we'd need to lift the box. If we put the box here, if the MA is 2, that means we only have to put in 2 newtons on this side to lift the box of 4 newtons. Remember, we've doubled our force, so whatever it is here, whatever we lift on the other side is twice as much. So what would our force be? 2 newtons to lift a 4 newton box. Now you don't get something for nothing. When you notice, if this lever tilts like this, look at how much difference there is between how far it would teeter on this side compared to this side. The box isn't going to come up very much when we put the lever down, okay? And so what happens is the drawback to getting a mechanical advantage is you don't get very much distance that it comes down.